Hello, everybody. Welcome to another guest speaker session with ML Healthcare Cohere. Today we have Harry Imad. Harry Imad is a PhD student in applied mathematics and theoretical physics at University of Cambridge. He is part of the Vandersher lab. His work primarily focuses on machine learning for healthcare and synthetic data, dynamic system simulation, inference, time adaptation of ML system. And today he's going to talk about his recent paper that is improving the generalization and evaluation of synthetic data for downstream medical causal inference. A brief description about what he's trying to talk about is medical data primarily is not available due to privacy issues, and in order to counter that, a good solution is using synthetic data, right? And using synthetic data involving causal inference. That's something that he's working on. He's going to present it today. And he's going to discuss about typical synthetic data generation methods, how to counter poor quality of data, misaligned metrics. And he's going to talk about a new evaluation metrics, how to make these frameworks more robust for medical causal inference. Over to you, Harry. Thank you so much for joining us today.
Great. Thank you very much. I'll just share my screen. Okay, hopefully you can all see that.
Yep.
So yeah, as Anna said, this is a presentation about my paper called Improving the Generation and Evaluation of Synthetic Data for Downstream Medical Causal Inference. This is a recent paper which we will be presenting next week at NeurIPS in San Diego, if anyone's there. We'll be in poster session, whatever it is, on Friday. And yeah, this was done by myself as first author and with some collaborators from Cambridge and from LMU Munich, and with my supervisor, Mihaela Vandersher. And yeah, I'm funded by Canon Medical Systems Corporation, who made this research possible. So, as Anas said, in medicine...
Excuse me, could you please hide the Google Meet thing on the right? It's a bit distracting from the slides.
Sorry.
You could just minimize that, yeah.
Yeah.
If you just click the cross button.
Yeah, you can cross that.
Yeah, good.
Okay,
Thank you.
Thanks for letting me know. Yeah, so data sharing in medicine is a very important process for a few reasons. It can facilitate innovation when if researchers have access to large medical data sets. Medical researchers can pursue and investigate different hypotheses which could be validated using that data, and it can facilitate innovation in the scientific discovery of new medicine. And it can also facilitate trust in the scientific process by allowing people to reproduce studies to see if they can discover the same conclusions that researchers may publish from the raw data that they have done it from. And this has been captured in a number of recent papers which are advocating for more data sharing in medicine and how it is an ethical imperative and how it will be crucial to improve and continue innovation in medicine. However, because of the sensitive nature of medical data, and it's particularly patient-level data, and the many regulations around it, including HIPAA regulations and GDPR in Europe, this can restrict the amount of data sharing that is allowed for research purposes, and this can make slow down the scientific process, really, and make that all the innovations that would be possible with easy data sharing much slower. And this isn't to say these regulations are not important, but it does certainly slow down scientific process in that respect. And synthetic data has some promise to alleviate these issues. And if you're unfamiliar with synthetic data, the general premise is that if we have a real data set which contains some statistical properties or some signal about something which an analyst may be interested in, but we cannot share this real data for privacy concerns, then it is often possible to make a synthetic copy of the real data using one of many methods. And this synthetic data is created in the hope that it will capture the important statistical correlations that are displayed in the real data, while preserving the privacy of the individuals that are described in the data. And then this synthetic data set can be shared in place of the real data, so that good analysis can still be done and enabled by this data without violating any regulations or privacy concerns. However, in general, this synthetic data will be an approximation of the real data. It will be drawn from typically a distribution which is learnt to approximate the real data distribution, and in general there will be some error in this approximation. So the synthetic data can be thought of as sort of a lossy copy of the real data. And there are ways that the data holder who holds the real data basically has a bunch of choices to make if they want to create a synthetic data set, and they can bias the creation of this synthetic data set in a certain number of ways, so it can favor the preservation of certain parts of the distribution or certain variables more than others. And basically, the way that this should be done is the data holder should consider how will this synthetic data be used, and what would be a useful synthetic data set for me to create, depending on the needs of the downstream analysts who will use that data for the most common purposes. But this notion of usefulness is really context dependent, and that's what we want to hammer home in this paper. So yeah, we can sort of see a pictogram of the typical synthetic data pipeline here, where this basically describes what I just said. A data holder will have access to some data set, real data set DR, and they will train some number of generative models, Q, and they will have some number of evaluation metrics, M, that they can assess the data produced by each generative model. And then basically they can measure the quality of the data sets produced by each of the generative models, and then release downstream the best data set and perhaps also the associated metrics, so that downstream users can have some idea of what is the level of quality of the synthetic data. But this process really needs some communication between the data holder and downstream analysts in terms of what it means for a data set to be useful. And this should guide the choice of the generative models that the data holder trains, and it should guide what metrics they use to describe the quality of the data set. Currently in synthetic data literature, and specifically we're focusing on tabular synthetic data here rather than image synthetic data or textual synthetic data or anything like that. The predominant downstream task considered for tabular synthetic data is the task of traditional supervised learning or predictive tasks. So this would be, a typical example of this would be some kind of, say, classification task where you have a synthetic data set which could be used to train a classifier, but it has some privacy issues. So you create a synthetic data set, release it, and then downstream analysts can train their own classification models or regression models or whatever supervised learning task they're interested in. And for the synthetic data set to be useful in this context of supervised learning, it's typically enough to preserve the associational dependencies between variables in the real data, so that a machine learning algorithm can still learn those correlations from the data. And because this is the typical use case that's considered in the bulk of the literature and many papers, the synthetic data models and metrics have been shaped to perform very well in this setting at the expense of other use cases. So in medicine in particular, there will be one particular class of variable in medical tabular data, which makes the downstream analysis of that data quite unique. And that is the treatment variable. So if we consider, say, a medical tabular data set of a hospital record book, which basically would record for each patient some number of covariates, which we describe as X here, which can describe the patient, and then some number of treatments, which are applied to the patient, and then some number of outcome variables which are used to measure the effect of the treatment according to what the patient's covariates were. So the conditional effect or the average effect or any number of treatment effect analyses. So because of that treatment variable invites this unique style of analysis by a family of methods called causal inference methods. And we can see here a simple sort of causal diagram of what this data may look like, where typically the covariates X have causal relationships to what treatment is assigned to a person, and then that treatment and also the covariates X will cause the outcomes that the patient displays. And it is these causal links specifically which are the target of a lot of medical causal inference analysis. So the analysis of this covariate to treatment link, causal link, is done when you want to, say, analyze treatment protocols or assignment analysis, which I've written here, and that is to study the cause, what causes doctors or practitioners to treat someone a certain way based on their covariates. And similarly, the effect of the treatment on outcome variables, this arrow from W to Y, as well as the arrow from X to Y, can be analyzed for treatment effect analysis. And that can either be done at the average level, so what is the expected treatment effect for an average patient, or the conditional average level, which would be what is the expected treatment effect for a patient with this level of covariates. And because these causal arrows are the target of such analyses, they should be well preserved in the synthetic data in particular. And this is different than the data requirements that typical supervised learning and prediction tasks place on data. So because this is a unique type of analysis that will be conducted on data, which is different than the norm in the synthetic data community, it has been sort of ignored somewhat by the research, which means that generation and evaluation methods for data with this use case are really lagging behind, despite the importance of such causal analyses for medical research. And basically it means that synthetic data is less useful in the medical setting, and it's also masked by being evaluated with metrics which really are not so meaningful for medical use cases. So even if the data is poor quality, it's quite hard to show that it's poor quality with the current evaluation metrics available. And this will just hinders the use of synthetic data in medicine overall. So really the purpose of this paper is to address this gap in the research, trying to bridge the gap between the needs of the causal medical inference community and the synthetic data generation and evaluation research. To do so, we establish a set of desiderata that we want synthetic data with treatments to maintain, and then we propose a principled way to evaluate such data and how well it adheres to these desiderata. And then we also propose a novel generation framework which optimizes directly for these desiderata and performs better than existing generators with respect to our evaluation metrics. So we'll start with the first point, which is how do we define what a good synthetic data set is for causal inference tasks? And this basically comes down to three key distributions, which are quite similar to the causal graph which I showed before. In causal analysis, there are three key distributions which really determine the effect of the analyses. And they are the covariate distribution, or P of X, the treatment assignment mechanism, P of W given X, and the outcome generation mechanism, P of Y given W and X. And these three key distributions are very important in causal analysis for the following reasons. So the covariate distribution in a medical sense really describes the population that the data represents. It describes the type of patient that is represented in the data set, and therefore it determines to whom the analysis on that data set will be relevant. So it's very important for a synthetic data set to preserve this covariate distribution as accurately as possible so that the analysis done on the synthetic data applies to the same class of people that it would have applied to if it had been done on the real data. And so, for example, if the synthetic data set fails to generate a particular part of the covariate space, then members of the population who exhibit that level of covariates will necessarily have to be excluded from downstream analysis. And on the other hand, if the synthetic data generates wildly out of distribution covariates, which are not supported by the real data set, then any analysis on the data will really not be grounded in the statistics displayed in the real data, which can lead to dangerous extrapolation. Secondly, the treatment assignment mechanism P of W given X is important in medical causal analysis because it is a target of analysis itself in assignment analysis and things of that nature, which is examining the link from X to W in the causal graph that I showed before. So if the goal of the downstream analyst is to investigate treatment policies displayed in data and see whether, say, different countries have different treatment policies or different doctors supply treatments differently or things, analysis of that nature, then misrepresentation of this distribution in particular in the synthetic data will poison such analysis. And the results of this analysis could be, say, if we find that doctors are supplying treatments to a certain type of person, then that might encourage more clinical trials of such treatments on that kind of person. But if in reality the analysis that we figured out from the synthetic data was false, then that can lead to dangerous experimentation of treatments on patient subsets where they would really never receive such treatments. Also, this distribution is used in downstream in treatment effect models as a nuisance parameter. So errors in its modeling can propagate to treatment effect errors as well. And the final of the third distributions that we really want to preserve well is the outcome generation mechanism. This is the link from the treatments and from the covariates to the eventual outcome of interest. And this is the distribution through which treatment effects can be estimated by comparing the statistical functionals when W equals 0 and when W equals 1, which is called treatment effect analysis or conditional treatment effect analysis. And therefore, its preservation is very important if we want to conduct treatment effect analysis on the synthetic data. So these three distributions are all uniquely important to preserve for the analysis that we conduct on the synthetic data to be valid. And also they completely decompose the joint distribution of the data if these three classes of variables are all that the data display. And we can see this decomposition here. And so therefore we claim that their preservation is both necessary for the previous reasons and sufficient, since they completely decompose the joint distribution for a synthetic data generator Q to be a high quality model of P in this use case for medical causal inference. And so therefore they establish our three desiderata. We want synthetic data to preserve the covariate distribution, to preserve the treatment effect, treatment assignment mechanism, and to preserve the outcome generation mechanism. So with that in mind, if we have these three desiderata, then this should shape the way that we evaluate how good a synthetic data set is. Now that we've defined what a good synthetic data set is, we should measure the adherence to each of these three categories to offer some assessment. And in other words, by evaluating how well each of the three previous distributions are preserved in a synthetic data set, we are essentially allowing an analyst to answer the following questions, which is question one would be, how representative are the patient covariates in D of S? That can be answered by assessing how well the covariate distribution is preserved. If we want to answer question two, which is how accurate are the treatment assignment decisions in the synthetic data, that can be answered by analyzing specifically the treatment assignment mechanism. And if we want to answer how much error might be introduced if in treatment effect estimates derived from the synthetic data, that can be answered by specifically assessing the outcome generation mechanism, or our third desiderata. So since synthetic data is quite a mature field, there are already many evaluation metrics which could be used and could potentially allow us to answer these three questions. However, because of the reasons I said before, that the field is really focused on downstream prediction and supervised learning tasks, there are not really guidelines in the literature for how to best assess the three distributions in particular that we care about. So we can see in this table what a lot of typical evaluation metrics, the class of evaluation that they fall into. So for example, a marginal evaluation metric would be some metric which basically compares each marginal distribution of the synthetic data with the real data. So for each variable in the distribution in the real data, it would compare the marginal of that variable in the synthetic data with the real data, with some divergence metric like KL divergence, or some other divergence metric like the Jensen-Shannon distance, for example. Other families of evaluation metrics are correlation metrics, which expand on marginal metrics by evaluating how well the two-way correlations between variables are preserved in the real and synthetic data, and this really scales up to the n-way correlations, 2, 3, 4, up to assessing the whole joint distribution, which is the next class of evaluation metrics. And then there's also a family of evaluation metrics called precision and recall metrics, which basically try and estimate the support of the synthetic and the real data and examine how much they overlap. But yeah, because the focus of the literature is largely on supervised learning and minimizing the difference between the joint distributions of the synthetic and the real data, no existing metrics advocate to individually assess the covariate distribution, the treatment assignment mechanism, and the outcome generation mechanism. They might be indirectly assessed via some of these metrics, but none of these metrics can cleanly answer the three questions that we posed before, because they do not differentiate between these three classes of variables as we would want them to. And we can prove that some of these metrics will really lose sensitivity, we term that here, to two of these particular distributions because of the relative dimensionality of the covariates in the data. So what this means is, if we consider the three classes of variables that we're concerned with, the covariates, the treatment, and the outcomes, the covariates in medical data tend to dominate the dimensionality. If you want to describe a patient, or if you want to examine a hospital record log of a patient, there can be hundreds or thousands of covariates which describe a person, but the number of treatments they receive will be much, much lower than that. And the outcome variables, the variables which are really important to determine the effect of a treatment, will also be much less. So given the covariates tend to dominate the dimensionality of medical data, evaluation metrics which assess the difference in joint distributions also tend to be dominated by how well the covariates are preserved. And they tend to lose sensitivity to the treatment assignment and outcome generation mechanisms because they form relatively small subsets of the data space. They are small in dimensionality, those two distributions. And we derive a theorem here which explicitly states that, which is, if we put some assumptions on the form of the real distribution P and some proposal distributions Q, which I won't necessarily go into here, but those assumptions are in the appendix of the paper, then if we measure the covariate, the KL divergence in particular between the real distribution and these two proposals, and we dictate that the proposal distributions can have an arbitrarily poor modeling of the outcome generation and the treatment assignment mechanisms in particular, but as long as they produce a reasonable modeling of the covariate distribution, then basically as we grow the number of variables in the data, the KL divergence will fail to pick up in any difference between two proposal distributions. Even if one perfectly models the, say, treatment assignment mechanism, and the second one fails to model that very well, the KL divergence will focus too much on the high dimensional covariate space and will fail to pick up this difference because the ratio of this metric between these two proposal distributions will tend to 1 as the dimensionality of the data tends to infinity. And this, while this is only true for the KL divergence in this theorem, and it only is true when D converges to infinity, in empirical analysis, we find that a similar result holds for a broad suite of joint distribution level metrics, and only at the level where, at a relatively small dimensionality where there's only 10 covariates. So this is not a phenomenon that will only arise in the extreme case. This can arise when the data set is still relatively small. We still see that basically what this table shows is amongst these 6 joint distribution level metrics. So this is precision, recall, Kale divergence, Kolmogorov, Smirnov, Wasserstein distance, and Jensen-Shannon distance. We can see that these 4 metrics really fail to reliably distinguish between these 4 proposal distributions, which we name the way that we produce the data here. The names are not necessarily important, but basically you can see that, or you should know that these 4 distributions are different, and we measure that truly with an oracle metric. And the only way that they differ is in the outcome generation mechanism. And we've designed them in a way so that we know that that's true. And the oracle metric, which is only measuring the outcome generation difference between these 4 distributions, can pick up that there is a true statistical difference between these 4 distributions. But because the outcome generation mechanism is only a one-dimensional part of the space, the data space, and the covariates are 10-dimensional, these joint distribution level metrics fail to pick up on the differences, and they've lost sensitivity to these to this distribution because they cannot really differentiate between these four proposals. So really, these metrics are quite poor for determining which synthetic data set is best for a medical use case. And so inspired by that realization, we designed our own suite of evaluation metrics, which do specifically target the 3 distributions which we said that we care about as part of our desiderata. And by differentiating out those 3 distributions rather than just measuring joint distribution distances, we can really circumvent that loss of sensitivity to the small distributions of treatment assignment and outcome generation. So as we said, evaluating the covariate distribution is still important, and that can be done via a number of ways, because this is a typical synthetic data evaluation task, really. Once we have chopped off the treatments and the outcome variables from our data, and we're just considering the synthetic and the real covariates, these are just high-dimensional matrices which we want to compare, which can be done by any family of the previous metrics which I just discussed. And that's fine because they no longer have treatments and outcomes. So it is fine to just consider the joint distributions between covariates. We choose specifically to use the integrated alpha precision and beta recall metrics, which were proposed in a paper maybe 3 or 4 years ago. And basically, these metrics operate by projecting the data into a subspace, which is a hypersphere, and then they calculate what's called the alpha support of that subspace, which is basically a sphere in the subspace of a certain radius, which captures a certain proportion of the data, which is alpha or beta here. And then they project both the real and the synthetic data into this hypersphere subspace, measure the difference between their alpha supports, and use this to craft a precision and recall metric. And basically what these metrics individually mean, a synthetic data set with high precision means that it generates data in the high density regions of the real data. So it means that all the synthetic data is highly realistic if the precision is high. If, on the other hand, the recall is high, it means the synthetic data generates data across the spectrum of the real data distribution. So it means that it really covers the real data distribution, and it doesn't ignore any parts of the distribution. So ideally, we would want a synthetic data distribution which has both high recall and precision. In practice, it tends to be that different generative models trade off between these 2 metrics differently, but it is possible to get high scores in both, where a high score would be 1 and a low score would be 0. To measure adherence to our second desiderata, we want to measure how well the treatment assignment mechanism is preserved in the synthetic data. And this can be done quite easily by training a classifier on the synthetic data set and training a classifier on the real data set. And this classifier is trained to classify what treatment will the patient receive based on their covariates. So it is learning that causal link between covariates and treatment. And then we want to measure the difference between these two classifiers, basically. And how we do that is specifically here, we measure the Jensen-Shannon distance between the two binomial distributions induced by these two classifiers, with the equation here for Jensen-Shannon distance. And the reason we choose this metric in particular to measure the difference between two classifiers is because it's bounded between 0 and 1, which gives us a nice reference of scale. If something is near 1, we know that it's good, whereas a metric which has no bound can be hard to determine what is sort of an absolutely good score versus just relative measurements. Because this is bounded between 0 and 1, if something is near 1, we know that it's good without needing to compare it to anything else. And similarly, to assess the outcome generation mechanism, which is our third desiderator, we train what is called a Kate estimator on the synthetic and the real data. A Kate estimator, or Kate, which is an abbreviation of conditional average treatment effect, is basically a family of estimators which are designed to estimate the treatment effect displayed in a data set. This can be done in a number of ways, but an easy way to do it would be to train a regressor on all data which, say, is the untreated data, and then all the data which is the treated data, to regress the outcome variable. And then you would predict the conditional average difference between the treated and untreated from these two regressors, and that would be the Kate estimate, or the treatment effect estimate. So that's one naive way to do it. There are more complicated Kate estimation techniques, which I won't go into here, but in general, they all estimate this average treatment effect, which is exactly comes from the outcome generation mechanism that we care about. So if we have good parity in these estimators trained on the real and synthetic data, we can be quite certain that the outcome generation mechanism is well preserved in the synthetic data, because it preserves the ability of the data to teach these models the treatment effect. So basically, we across a family of learners, which is described as F here, we train these learners on the synthetic and the real data, and we measure their difference, their expected mean squared error. And so that covers our suite of evaluation metrics. And now I'll quickly get into the other part of our paper, which is answers our final question, which is, now that we know how to measure data and we've defined what's good, synthetic data, we've defined how to measure it, and now how can we generate data so that it performs well in terms of our desiderata and maximizes these metrics. So again, we first look at typical generation mechanisms, which fall into two broad families. So we can define this family of generic generative models, which is probably what most of you are familiar with, like GANs, diffusion models, VAEs, normalizing flows, etc., flow matching models, and so on. Basically, any model which tries to minimize the joint distribution between the synthetic and the real data via some training mechanism, we would class as a generic generative model. Basically, these models place no assumptions on the data, and they just try and minimize the joint distributions, the difference in the joint distributions. And this is very useful for the task of prediction, as I said before. There is also an existing family of models called causal generative models, which are more closely related to our task here, but place some more restrictive assumptions on the data generating process than we do. So a causal generative model will typically assume access to a full causal graph, which describes the causal relationships between every single variable in our data set. And then it will learn to generate data faithfully according to this causal graph by, say, generating the parent variable of the causal graph and then propagating that through the graph until eventually they end up with samples from the joint distribution. However, as I said, this requires knowledge of the full causal graph, which in complex settings with high numbers of variables, which is exactly the setting we want to operate in, where, say, the covariate dimensionality is very high, it can be almost impossible to know what the true causal graph is. So this is an assumption that's rarely true in practice in medicine. And so generation with these methods is hindered because of that. In comparison, we propose a sort of hybrid architecture between the two, which assumes that the data is generated via this causal generating process, which has some causal graph, but it doesn't assume access to the entire causal graph. Particularly, it doesn't assume access to the causal links amongst covariates. And we call this the STEAM framework, which is useful for generating synthetic data for treatment effect analysis in medicine. And basically, we wanted this generation framework to mimic the real data generation process that we see medical data exhibit. And this is shown in this flowchart here, basically, where we generate the covariates, then we generate the treatments, and then we generate the outcomes in a three-step fashion. And the way that we design this framework is such that it is really method agnostic. The three models that we use as Q of X, QW given X, and QY given X and W are interchangeable. Really, you can set basically any generative model as Q, as the first Q of X, and then you can set any classifier to generate the treatments as Q of W given X, and then any regressors as Q of Y given X and W. And we experiment on a broad suite of different choices. And basically, we see that as long as we follow this general pipeline for generation, our metrics will perform better than if we try to generate according to the earlier joint or causal models. And we can see that in the next two slides. These are quite big tables, but I'll just basically, you can see a lot of green in this table. And what that means is that we're comparing in this pipeline, we set QW given X as a logistic regression classifier and Q of Y given X and W as the simple Kate estimator that I described earlier, where we train it on treated and untreated and then just measure the difference as the Kate. And we set those throughout the experiments in this table. And basically what we're doing is changing Q of X, changing the generative model in this, and comparing it to as if we had just generated the data with the base generative model Q of X and not done the three-step-wise generation process that we've described, but done generic generation. And what we can see is that each STEAM model, which is described as STEAM and then subscript of the generative model that it uses within it, improves on our metrics compared to the base generative model just generating by itself. So we can see that giving it this framework for how to generate closer to the true data generating process does improve on each of our metrics. Specifically, it improves most on the treatment assignment and outcome generation metrics, so JSD pi and UPHA. We see the biggest differences there, whereas the covariate metrics are only marginally better. And this is because, as I said before, the covariate dimensionality tends to dominate the medical data distributions that we are experimenting on here. And so that means that these small distributions of treatment assignment and outcome generation tend to get lost in joint distribution generators. And when we preserve some model capacity for them by doing our three-step generation, where we focus specifically on those smaller distributions in steps 2 and 3, we can really get a lot of benefit, and our metrics are much better on those two dimensions there. This is also true when we compare to different causal generative models as well. So this was the generic generative models. This is causal generative models, where in this case, red is good for our method, where we compare the best STEAM models from the previous graph here to a number of different causal models, and we see that they perform worse in general than the STEAM models for the same sort of reasons. And finally, we have some results that show that, as we hypothesized, the performance gap improves when it becomes harder and harder to model those small distributions of treatment assignment and outcome generation mechanisms. Because joint level generators, will not focus on these small distributions, whereas the STEAM model does. So we can see that when we grow the dimensionality of the data from 5 variables to 50 variables, STEAM, the quality of the data degrades in both cases, but it degrades far worse for generic generators than STEAM generators. And similarly, when we increase the complexity of the treatment assignment mechanism, so this is basically, we have a simulated data set where we increase the number of covariates that the true treatment assignment depends on. as the number of covariates k increases in this equation, the STEAM performance stays pretty stable, whereas generic generative models struggle to capture this more and more complex distribution. And this is the exact same setup, except now we vary the number of covariates that the outcome generation mechanism depends on. And we see again that STEAM can capture these more complex distributions, but generic generative models perform much worse as they become more complex. And that's because, again, their capacity is lost on the high dimensional covariate distribution rather than focusing on these small but important distributions for causal analysis. Yeah, so that comes to the end of the main body of the paper. I might stop the presentation here. There are a lot of other experiments in the paper, in the appendix. There's quite an extensive appendix where we do some proofs on differential privacy, which is a kind of provably private generation. We do some initial experiments in that setting. And then we also test out different classifiers and regressors rather than just the different generative models. But yeah, those are the main takeaways from the paper. So happy to take any questions if anyone's got any.
Thank you so much, Harry. Really, really interesting work. Anybody has any questions? Please go ahead. I have a few questions. Maybe you can start from that. So in the STEAM model, right, you have the Q of X, Q of W of X, and so could you explain like the role of each of those distributions in the STEAM model?
Yep, I'll share my screen again. So yeah, a typical STEAM model has this generation flow where this bottom row shows the real data that we supply to train the models. And then, yeah, Q of X, QW of X, and QY given X and W are three machine learning models which target each of these distributions individually. So Q of X is basically any generative model which can generate covariates of arbitrary dimensionality. And we train that just to mimic the covariate distribution of the real data without worrying about the treatments or the outcomes. And that, yeah, is any generative model, basically. Then Q of W given X is designed to specifically mimic the treatment assignment decisions of the real data. And so this is a one-dimensional conditional distribution. So this is any model that can generate a one-dimensional variable conditioned on all the covariates. So in this case, we set that as a logistic regression classifier, where it will generate the most probable treatment that synthetic patient would be assigned based on its training of the real data. And then similarly for QY given X and W, this will generate the outcome variable Y based on which is also one-dimensional in our use cases here and continuous in this case. So it's a regression task based on the high-dimensional covariates and the treatment. So this can be any family of regressors can be set in this class of model. And then we generate data in this three-step fashion shown in the flow. So we generate the synthetic covariates, then we assign them the most likely treatments that they would have received with the classifier, and then we generate the outcomes from the regressor.
Got it. So instead of like using to model these three components separately, can we use them like approximate doing the joint distribution of Q of X, Q of W, and Q of Y?
Yes. So this three-step generation process will approximate the joint distribution because it generates X, W, and Y just separately. But at the end, you use all of the data. And we find that because like a generic generator, which is shown here, will also generate X, W, and Y, but it generates it all at once by learning the joint distribution. Because we impose this three-step process, with basically we're forcing more model capacity to be assigned to the treatment and the outcome variables, which are only one-dimensional, whereas in the joint distribution case, there's no easy way to force these joint distribution models to typically specifically focus on those one-dimensional conditional distributions. So there's inadequate model capacity is given to those small but important distributions, if that makes sense.
Yeah, that makes sense. Thanks, Eric. Appreciate it. Anybody has any other questions? All right. I think we can wrap it up if nobody has any other questions. Harry, thank you so much for taking out time and giving this talk today. We really appreciate it. People who would like to reach out to you, could you like give them some guidance? Like how can they reach out to you regarding collaborations or any other stuff?
Yeah, sure. I'm on LinkedIn as Harry Ahmad, or you can find me harryahmad@gmail.com if you want to send me an email. But yeah, definitely keen. If this sparked any interests in collaboration with anyone, please reach out. I'll also be at Neurops next week if anyone's there. So yeah, come by in San Diego.
All right. Thank you so much, everybody, for joining us today. Thank you, Harry. See
Thanks.
you in San Diego next week.
See ya.